Yeah, so hello everyone. We will start with a quiz, and it starts at 9:33. So we have 3 minutes for others to log in, and you try this quiz. And I think the quiz, yeah, essentially you have 10 minutes, but try to do this before because I will not wait for 10 minutes. Okay. So what I'm hoping is within 5 minutes you will reply, and then I will start the course in 5 minutes. So you try this quiz. These are simple quizzes, so you should be able to do this rather quickly. Okay. So um, okay. So I believe you should be able to start this quiz. Yeah, you can check the grade scope and see if you can see this quiz. So once you start this quiz, I think the time limit will be given to you in the form. So the thing is like you can start this quiz a bit later, but then the time limit is only like 5 minutes or so. So
Sir, there is no quiz in the grade scope right now.
yeah. So I mean I said at 9:33, right? So my computer timestamp is 9:32. So I think at 9:33 it should open.
Yeah.
Yeah, it is available now.
Yeah. So remember, once you start this, you have five minutes. So once you start, then it's 5 minutes. But those who start, let us say after 3-4 minutes, they still get 5 minutes from where they start. But then it ends surely at 9:43. Okay, so we can continue with the course. So this is the plan for today. Sorry.
Can you give five more minutes? I couldn't
Give,
lol.
we give 5 minutes. I don't think, because the quiz ends at. Look, quiz is an independent thing. I have to continue with the course. Okay, so I cannot. So if you have done the quiz, it's fine. If you have not done, it's something you have to deal with, right?
So I couldn't settle my grade score properly.
Sorry.
Like I couldn't settle my grade score properly.
So okay, that's not my issue.
Can you just
So
extend by 2 minutes?
I cannot take these things right now. Okay, if you have done, I have seen almost close to 200 submissions already. So those who have not been able to do, we will talk about this later. But that's not the point right now to discuss this in the lecture. Okay. Okay. So let us continue with the lecture, and turn off your microphone, please. So we will continue with the lecture class. Okay. And any issue, we will discuss it later. Okay. So we will discuss today spatial distributions. Okay. So and in the discrete case. Okay. So in the discrete case. In the discrete case, okay. So in the discrete case, what we have said is that the PMF is the distribution. Okay, that's something we have defined it. That is something we have mentioned this in the last class, that the PMF, okay, is the distribution for the discrete case. We also call this PMF to be the distribution, but remember that there is something called CDF, okay, cumulative. So that is also called distribution, okay. But so that is more commonly called as just as distribution, okay. So people, when they call distribution, it's usually CDF. But for discrete case, PMF is also called distribution. Of course, for PMF also there exists CDF. Okay, so these are just things that you will get in the context of when someone is talking about CDF or PMF. I have not defined CDF yet, so we will see. So so distributions in our case are nothing but PMF, and PMF is something we know. Okay, so PMF is like probability that x is equal to k for various values of k for the random variable. Okay, so that is called PMF, and we are interested in introducing spatial cases of random variables. Okay, so spatial random random variables corresponding to spatial distributions. And the reason to do this is the reason for doing this is to make things like to keep a template in hand, such that if I have some applications in mind, then I can say, okay, this belongs to one of these distributions. And then for that, I know many things. Like I have studied this, let us say I know all this for 5 distributions, and then I can make some quick observations. Okay, so so let us see. The first distribution for us will be the uniform distribution. Okay, so let us see some motivating examples. So this is something we have seen already. So consider rolling a fair die. The possible outcomes are 1, 2, 3, 4, 5, 6. Okay, that's the outcomes. Then the PMF is given by this. Okay, so our random variable x takes these values, and the PMF, the probability that I get x equals to 1 is 1 over 6. Probability for x equals to 2 is also 1 over 6. Probability that x equals to 3 and so on is always 1 over 6. And for any other cases, we just define it to be 0. Okay. So we note here also that here should be px. Okay. So we also note that if we sum over PMF of x, right? So this is like 1 over 6 plus. So this is here, and then this is another term which is also 1 over 6. So if we do this, then it sums to 1. So in general, we have also seen that PMF, if we sum over x, it must be 1. Okay. So so this can be verified for each PMF. In fact, this is a good criteria, a good check for validating a PMF. Okay, so if I give you a distribution and I ask you to write a PMF, one of the things that you should check in your PMF is that it must sum to 1. If it is not summing up to 1, then there is something wrong in the PMF. Okay, so what we note here is that PMF takes uniform values for all values of x is equals to x. So this is the uniform value. Okay, so this is the uniform values it's taking for all values of x. Okay, so that's why we call this uniform distribution. Okay, so any experiment that you consider that in which any outcome has a uniform probability, like the same probability for all the outcomes, then that is called uniform distribution. Okay, so everything with this criteria, we will put that into uniform distribution. So there will be many things, right? Even coin toss, okay, half. Okay, so that also comes under the category of uniform distribution. Okay, so this is uniform distribution. So now we can formally define uniform distribution. So motivated from the previous example, we now define uniform distribution on 1 to n, let us say. Okay, so we have this. Obviously, we will not define it up to like for infinite or so on. Okay, so we define it for n let us say outcomes. Okay, and in this case, for each outcome, the probability is 1 over n. So uniform distributions is very simple to predict what would be the probability, right? Someone tells me it's already a uniform distribution, then probability of any outcome is just 1 over the number of outcomes. Okay, so total number of outcomes. So in this case, it's n. And in this case, again, we can verify that, again, I missed this. So sum over PMF must be equal to 1. Okay, so that's uniform distribution. Okay, now I can define something called Bernoulli distribution. So Bernoulli distribution, you can think of unfair coin. And let us say probability of head is P and probability of tail is 1 minus P. Okay. So such kind of experiments where you have two outcomes, okay, let us say success or failure, pass or fail, okay, with some probability, general probability P, okay, then those kind of experiments you will put in Bernoulli. Anything that has two outcomes with some probability, okay, this also includes the equal probability case, right? So if it is equal, then it will go towards uniform, okay, so that's the point. If P is half, then for x equals 0, it's half. For x equal to 1, it's half. So it is just uniform. Okay. So any cases where you have binary outcome 1, 0, okay, and heads and tail or so on, that we all collect these things into Bernoulli random variable. So Bernoulli random variable can be defined as the PMF of that can be defined as if the first outcome is 1 and then it's P, the second outcome is 0, then it's 1 minus P. So 1 could be, let us say, heads, 0 can be tail, it could be pass, okay, it could be fail, okay, it could be success, it could be failure, okay. You can put H to be 0 and tail to be 1, it doesn't matter, it's just a symbol here, okay, and then it's 0 otherwise. And the probability, we know that we would like to take this between 0 and 1, okay, because if we include boundary cases, then other one becomes 0 automatically. So that is not a Bernoulli. Bernoulli, we need at least 2 branches, not at least 2, but exactly 2 branches with some greater than 0 probability, because if it's 0, then you are just essentially following one branch, and that's not Bernoulli, okay. So we have P greater than 0, less than 1. So as I said, it must have 2 possible outcomes. For example, pass or fail, or heads or tail, or any binary outcome you can think of. Okay. Next is something called geometric distribution. Okay, these are the probabilities we have computed before. Okay, so these are not strange to us. It's just that we are now making templates now, and then nicely putting them and giving them some nice names so that we will not forget this when we are. When we encounter some real life problems, then we can immediately say, oh, okay, this is geometric. Okay, this is like Bernoulli and so on. So this is geometric. Now geometric like you can already guess which type of problems it can denote, right? So if you recall which were the problems where we were doing like this, right? So can you recall like which type of problems had probabilities like this, right? So we have done good type of good practice with this type of problem, right? So it's like something with probability 1 minus p k minus 1 times, okay, and then something happening at the kth step. Okay, so that's what we had, right? So it's like getting a first head at the kth step. Okay, so it's like saying first head at kth toss. Okay, or you can make this into anything arbitrary, right? What is something that happens for the first time at the kth trial? Okay, so an event that happens for the first time at kth step. Okay, so a kth step or trial or okay. So you can generalize this to any problem now, not just to coin tosses. Okay, so it could be any I think, but important thing to note here is that here again it's like a two likely cases. Okay, so it's like if I toss a coin, then I have like only two branches, p and 1 minus p. Okay, so here again these are the experiments where you have only two outcomes. Okay, something happens or something doesn't happen. I mean, it does not happen or like the alternative thing happens, but there are only two choices, like either head happens or tail happens. Okay, so this is also in those categories. So when you see experiments like this, where the experimental outcome is always binary. Okay, so that's also necessary for geometry. It's binary, and it's something that happens for the first time at the kth trial. Okay, so that's geometric. Okay, so once again between 0 and 1 it makes it makes sense here. So for instance, as I said, coin toss is a very familiar example. We have done this before. So some books also define geometric random variable as a total number of failures before observing first success. Okay, so as I said, like it could be success or failure. So total number of failures. So let us say how many failures you had, right? So let us say if we translate this, then this means like let us say k minus 1 failures and success at kth step. Okay, k minus failure success at kth step. But if we define it like this, total number of failures before observing the first success, then it means like the random variable where you're talking about x equals to k. This means like first I have seen the k failures, and then at the k plus 1th step I have success. Okay, that's the only difference when you see like this. When I'm saying total number of tosses, when I got the first head, then I got the first head because the random variable is the total number of tosses. So that will include the kth, right? But when you define like this, total number of failures, so it's like your k stops here. You have seen total number of failures, then at the kth plus 1 step, you have the success. So that's why there is a slight change here sometimes in the book. So you have seen total number of failures, so which is k, and then you have seen the success at the k plus 1th step. Okay, so that's why there is a slight difference. So you can see, I mean, these are just common sense. So you can, when dealing with problem, you know what to do. So it's just a notation thing, right? K is just arbitrary here. Okay, so then next distribution that we are interested in is something called binomial distribution. Okay, so random variable x is called binomial with parameters n and p. Okay, so this is denoted by this x is binomial n comma p if the PMF is given by this. Okay, so this is also we have done before when we were doing probability using counting arguments and so on. So you can guess already like what this probability stands for, which type of events, right? So which type of events this probability stands for. So by looking at this term, we can already say it's like asking for okay, so it's like asking for something that is like k times and something that is happening n minus k times, right? So somewhere like I have something that is happening k times and remaining ones are happening n minus 1 n minus k times. Okay, so this it relates to what we have done before, right? So this is like these are like p. Okay, so k times and remaining ones are n minus p. So these guys are n minus k, sorry. Okay, so 1 minus p to the n minus k, and these guys are p to the k. So this tells us like possible events for this are like getting exactly k hats in n trial, right? So this is like k hats in n trials. Okay, so these are the things we have discussed this also during counting, and ordering doesn't matter. So p the heads can be, so ordering of heads doesn't matter, right? So p can be in any way. So this stands for that. N choose k. It's like I can put them in any way I want. So n choose k, p to the k, 1 minus p to the n minus k. Okay. So this again corresponds to events that have only two outcomes, like heads or tail. So and so on. Okay. So PMF for this is given by this. Okay. So this is also we are familiar with. So consider an unfair coin. Consider tossing the coin n times and let x be the total number of heads we observe. Then x is the binomial with parameters n and p. Okay, so p is the probability of the heads, let us say. Okay, so probability that I obtain probability that I have obtain one heads in n trial, probability that I obtain two heads in n trial, and so on. So these are the probabilities given by this. Okay, so are binomial and Bernoulli related? Remember, Bernoulli was what? P when x equals to 1. Okay, and 1 minus p when x equals to 0, right? So this was the Bernoulli, and this is p. Okay, because in Bernoulli n is like fixed to be 1, right? So now you can already see what I'm trying to say, right? So so Bernoulli and binomial are related, right? So Bernoulli is like binomial with n equals to 1, right? So and so in other words, other way to say is this: I do Bernoulli n times. Okay, I do Bernoulli n times. Then, so Bernoulli is like just one coin toss, and binomial is like n coin toss. You need to do n trials. Okay, so it seems like I can simulate binomial by Bernoulli. So Bernoulli I do repeatedly n times. And then I may ask from there how many, what is the probability that I got certain number of heads and so on. Then I can get it from there. Okay, so it is now evident that if x1, x2, xn are independent Bernoulli random variables, then the sum will have. Okay, I think there is something wrong here. So sum will have binomial distribution. Okay, so that is like intuitively clear, but we can prove this as well. Okay, and another thing is like we verify that. So proof of this, I'm not doing this now. Okay, so maybe I will also post this as an assignment. These are the good things for assignments, and we can also verify that the sum of the PMF. Okay, sometimes I'm using p and sometimes I'm okay. So let us say this. So sum of these p values will be 1. So this is also you can check. Okay, for sum over x equals to 0 to n. Okay, so I have also started using x, but here it was k. Okay, but it doesn't matter. Okay, so this sum will be 1. Okay. Okay, so this is one example. Let x be the binomial n comma p, and let another random variable y be the binomial m comma p, be the two independent random variables, we define the random variable z to be x plus y. So what do you think will be the PMF of z? Okay, so let us take one random variable x, another random variable y. We sum the random variables. So what will be the PMF of z? Okay, so this is what we are like. So what do we think, right? So how do we, what would be the PMF of z? So what we noticed from the previous observation, like this one, is if I take n independent Bernoulli, okay, then this has, the sum has the binomial distribution. Okay, so this is something we know. Okay, so corresponding to each binomial, we have n independent Bernoulli. Independent, I can see this as n independent Bernoulli, and here I can see this as m independent Bernoulli. Okay, so this means that x can be written as let us say x1 plus x2 plus xn, where xi's are Bernoulli. Okay, and also we have y is binomial, so y binomial over m, so y will be y1 plus y2 plus ym, where yi's are Bernoulli. Okay, now if I add it, then by induction I can claim. Okay, by induction I can claim that the whole thing will be Bernoulli. So x plus y, which is z, which is x1 plus x2 plus x3 plus dot 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 plus xn plus y1 plus ym. Okay, so so these are all independent, right? So I can treat them. Okay, but like I can treat them as, because these are sum of m plus n independent Bernoulli random variable. Okay, so from the previous argument, this must be binomial of m plus n, and p is the same, right? So probability is kept the same, right? So that doesn't change. Okay, so so if there are two binomial given to us, then the sum will be also binomial. Okay, now let us look into something called Poisson distribution. Okay, so what we have seen so far, we started with uniform. Okay, so the outputs take uniform probability values, same probability values, those are classified into uniform. Then we saw Bernoulli. Bernoulli are those cases where we have like head or tail type of events, pass or fail, success, failure, and so on. But it's just one trial. Okay, so Bernoulli is just one. Yes.
Could you please explain why how Bernoulli and binomial is related again?
Bernoulli and
binomial.
Yeah. So what I have left for you is to prove this claim, right? So if x1, x2, xn are independent Bernoulli, then if you sum this, then it will be a binomial. Okay, so you take the Bernoulli random variables x1, x2, okay, and like you can take only two, let us say, okay, and then you can prove that. So if I sum this x1 plus x2, okay, then it must be the variable I get, it must be binomial 2 comma p. Okay, so this is something. So what you have to prove is that the PMF of this sum will be binomial PMF with k equals to 2 here. Okay, so I mean not k equal to 2 but n equal to 2. Okay, so this is something you have to do this calculation. Okay, so if I take 2 Bernoulli, then the sum of the PMF of the sum is binomial. Okay, so you try to do this And if you do this, then you know how they are related. Okay, then you know how to, because once I get the PMF to be same as what is described here. Okay, the way we define is like this: any random variable you come up with, and if its PMF is this, immediately it becomes binomial. Okay. So if you do this and if you get the PMF, then you immediately know that, okay, I can, if I add Bernoulli, I get binomial. Okay. So Bernoulli is like one, we are asking for what is the probability of getting an head, one trial. Okay, that's Bernoulli. Now, if I do another trial, I know that another trial is independent of the previous trial. I know that yet another trial is independent of the previous two, and so on. Okay, so if I do n of the coin tosses, they are all independent. They don't influence each other. Now, if I'm asking for k heads in n trials, okay, that is exactly the binomial that we are talking about. So binomial is nothing but n independent Bernoulli. Okay, so that's what it means. Okay, so the fact that they are independent has to be taken into consideration. So if you are in an experiment where the first toss influences the second, then it will not be binomial. Okay, so so motivation for Poisson. So, and then we talked about uniform, and then Bernoulli. Then from Bernoulli we went into binomial because we did n trials. And then yeah, so that's what we did. And then now we are into Poisson distribution. Poisson distribution is a little bit interesting because it uses discrete PMF to predict something in the continuous case. Okay, that makes it a little bit interesting. So let us see what it means. So imagine you are an Uber driver. Okay, and if you're an Uber driver, you need to maximize the profit. Okay, you want to remain close to an area with more requests from the customer, right? So Uber usually will send messages to those cabs that are around certain area, right? So you may want to be in an area where it has more requests. How can you use probability to predict requests in an area for certain car ride? Okay, so imagine that you are trying to solve this problem, given that there are on average 5 requests for a car ride per minute. Okay, this is given to you. On average, you have 5 requests for car ride per minute from certain area. So what you are given is an average. Okay, what is the probability of k request from this area in next 1 minute? Okay, so what is the probability of k request? And we are talking about probability. Okay, it's about probability. It's not just, I'm not just asking for request. You can say that, okay, on average 5 requests for car ride per minute. So in next 1 minute, I will get on average 5 requests, right? We are not just into average right now. We are talking about probability of k request in next 1 minute. Okay, so let us see how we can answer things like this or model this as a probability problem. Yeah, so this was our problem, right? Average 5 requests for a car ride per minute from a certain area, and we have to kind of, so what do we know for this problem? Okay, let us think, what do we know for this problem? There are requests for a car ride. So in the problem, we mention things like requests. Okay, so there could be a request, there may not be a request. Okay, so there are like 2 possibilities here, right? So there are 2 possibilities, request or no request. Okay, now this goes into the case of the binary, right? So we always want to relate our problem into something that we already know, right? So this seems to be like this is an experiment where there are like 2 possible outcomes, either there are request or no request. Okay, so okay, and then this sounds familiar. Okay, for example, how many heads in n trials and so on, right? So in this case, either there are heads or no heads. In this case, we are asking for how many requests. Okay, but there is something not very clear, because there is something with respect to the time here. Okay, and here what we know is like how many heads in n trials and so on, right? So it's the bins that we had were kind of n bins we had in hand, but we don't seem to have such bins like this. Like it's similar to saying like n, let us say k hats, but in 1 minute. It doesn't look like very similar to what we know, right? Previously, we know like how many hats, like how it is the probability that k hats in n trial, right? But there is no such concept here right now. It's asking for k request in 1 minute. Okay, so what do we do? Like can we take n to be 1? No, that doesn't make sense, right? Because in 1 minute I can have multiple requests, right? So, but can we do something around this? Okay. Well, the problem here is we don't have n trials. Indeed, a time interval, right? So we are given a time interval, not necessarily like n trials we had in the binomial. So what do we do? Well, the key idea is we want to use still the discrete distribution, let us say, but time interval is a continuous interval, right? So it's like between 0 and 1. So there are like infinite many things, and many requests may come simultaneously at one time. Okay, it's like depends on what you call instant time. Okay, it's like a nanosecond, whatever you call. I mean, time can be split into infinitely many times, right? So we cannot. We don't have the bins like we have in the binomial, right? N bins, and then we talk about in this bin something happens or not, or other bin something happens or not, and then we calculate from there. But here it's not the case. Okay, that's the difference here. So what does your intuition suggest, right? I still want to use, let us say, discrete distribution. So how can I go about, in some sense, approaching via discrete? Right, so let us say I want to approach this problem via discrete approximation. So what should I do? Right, what does your intuition say? So what does your intuition say? Like I still want to. I have given you a lot of hint actually. Actually, even the answer is right there. So it should be like something approximate to start with, but we may refine it right later on. So how do you do this, right? So to do this, well, it's always good to follow your intuition. So what this is saying is like, oh, it's asking for 1 minute. What if I make a bin from there? Like I make certain amount of bin. I understand that simultaneously many requests for car can come instantaneously. But I want to approximate this. Okay, I want to approximate this problem by binomial. So I will divide my time interval into bins. Okay, by bin I mean like the smaller time interval. So 1 minute is equivalent to like, let us say, 60 seconds, and 1 second can be broken into milliseconds. So it depends on like what you want now. Okay, so we get the idea now. Like we want to approximate this problem via binomial. We will approximate it by bin, right? So let us say this is the bin that I have calculated, and let us say these are the 60 seconds, and this is the first second, this is the second, and so on. And let us say this is the 60th second. Okay, so I am trying to approach this problem via binomial, and I have divided this 1 minute into 60 seconds. Okay, and hence I get these 60 bins, and now I can say, okay, in the first second I get the request or not. Okay, 0. Okay, let us say I didn't get the request. Okay, and then I in the second okay, I say whether I get the request or not. So let us say I didn't get. In the third one I got the request. Okay, and in the fourth one I didn't get, and so on. So you see how we have modeled this problem using discrete, but there remains a challenge. The challenge is even within 1 second. Let us say in this second I got 1 request, but it could have been that I got 5 requests in this bin itself, right? So we can still be in problem, and the reason why we cannot accommodate 5 is like in binomial we are only allowed 0 or 1. Okay, so 0 or 1 in binomial. So So this is our restriction. So we only have possibility of 0 or 1 in the bin, right? So another possibility could be is like we refine our bin more. Okay, so that's another possibility. Like just we want to refine it more, because maybe let us say millisecond. So we will define each second into millisecond. Let us say further partition of this into millisecond, and then we will say, okay, now I may be almost sure that within 1 millisecond there is only possibility of getting one request, okay, or no request. Okay, so this is the approach we are trying to do. We are trying to approach this problem via binomial. Okay, so we can break the minute into second. That's what I just said. Each second is independent trial with request or no request. Let x be the number of requests in a minute. Okay, so let us say x be the number of requests in a minute. Then in this case, let us say even for this, even with this, let us say we are approximating our problem. It could have been that I have received 2 requests and so on, but we will assume just 1, okay, because this is the partition of time we did. And let us go with this. If we do this, then if we model our problem like this with this granularity, and on average we are given that we get 5 requests for a car ride per minute. Okay, so this is average thing is given. So remember, expectance is the average. Okay, and which is the, in our case, let us say is denoted by some lambda. Then this expectance is n times p. Right? Why expectance is n times p? Because this is like a binomial, right? So it's like you are asking for it's like asking for n. It's like asking for it's like sum of p n times. Okay, so it's like sum of p n times. So so yeah, n is the number of trials, right? No, is n number of trials? No, n has to be number of request, I think. Yeah, n has to be number of requests, because so it's like asking how many heads I get. Let us say how many heads I get. So these are, let us say, the heads. Okay, in let us say k trials, right? So then if this is like binomial of let us say n, and how many requests I get. Okay, so let us say okay. Oh, okay, so this is like k is here and p is here. Okay, so the k is here and p is here. So if I compute the expectance of the binomial random variable with this parameter, then I will get np. Okay. So if we look into the binomial and compute the expectance, then we should have expectance to be np. I hope nothing is missing here. Okay, let's see if there is something, I will fix this. Okay, but let us keep this as lambda is some np. Okay, where p is the probability of whether the request comes or not. Okay, I will fix n if it is not correct now. Okay, so let us continue with this. Okay, yeah. So in this case, actually n is 60. Okay, so there are 60 bins. Okay, so n stands for 60. Okay, so n stands for 60, and the probability of, and the p can be computed as this. So 5 heads. Okay, let us say heads out of 50 outcomes, right? So this probability can also be calculated in this case, right? But I'm again not sure. I have 60 trials, right? I have 60, so why not it's 60? Five out of Oh, okay, so from here you computed this. Okay, so n is 60. Yeah, so this should be 60 actually, right? So p should be 60. P is 5 by n. N we are taking it to be 60. Okay, the 60 bins that we have, and 5 by n. Okay. Okay, so let us continue with this. So this is the binomial, right? So do we relate this now? Okay, so it's like we have 60 bins. Okay, so so we have 60 bins, and then we have P, which is 5 over 60. Okay, which is calculated from here. Okay, so so the binomial from binomial we get this, right? So probability that we have exactly k request now. Okay, so if we have k request, then this comes from this. Okay, because so in this case these are the k requests we are talking about. So k request out of the n trials. Okay, so we have in our case n is 60, so it's like in 60 seconds how many requests for a car we are getting. Okay, so we model this like this, but as I said before, restricting it to 60 bin is a problem for us because it may happen that within 1 second I may have multiple requests, so I may want to increase the bins further. Okay. Okay, so this is what we have written so far. So there is a problem. Problem is, what is that? So the time is continuous, right? So time is continuous. We cannot restrict them into 60 bins. Okay. So since time is continuous, no guarantee that there will be only one request per second. What do we do now? We can make the interval smaller. Take times intervals as milliseconds, but still there is no guarantee that there will be only one request per millisecond. What should we do next? Well, here comes the calculus. Okay, so here the calculus comes in the sense that we have to increase the bins now. Okay, so we have to increase the bins. In other words, we have to do the limiting process. Okay, we have to take the limits. Okay, we have to go from now. So using the discrete, we can go into the continuous case using the limiting process. That's what we have studied in calculus, right? So what do we do now? Okay, so we can take n tends to infinity, right? So so if we take n tends to infinity, what do we have? Right. So probability that this is the one. These are the results we have, right? I mean, this is the formula we have. So let me write down this formula. Okay, so this is like nk and then lambda. So this is like nk lambda n to the k 1 minus lambda by n minus k. Okay, so this is what I will write down here. Okay, so probability that x equals to k is, so I want to do the limiting process. I want to let n tends to infinity, n choose k and lambda by n. Okay, so this is divided, okay, k and then 1 minus lambda by n minus k, right? So if we expand this, then this is limit n tends to infinity n factorial by k factorial n minus k factorial lambda to the k by n to the k 1 minus lambda by n to the n and divided by 1 minus lambda by n to the k. So this will be limit of n tends to infinity. And if you do the simplification and so on, after this I am left with n minus k plus 1 divided by n to the k, n minus k factorial by n minus k factorial. I did a lot of simplifications and then I got k factorial, and all this boils down to limit of n tends to infinity n to the k by n to the k lambda to the k by k factorial and Okay, and here what I'm missing is so if you do this limit n tends to infinity, this becomes e to the minus lambda. Okay, from calculus, limit n tends to infinity, this becomes this. Okay, so e to the minus lambda, and what I'm missing is lambda by n to the k. So if you simplify all this and do everything, what you will end up with is lambda to the k by k factorial e to the minus lambda. Okay, so this is this we have obtained by using the limiting process. So this becomes so-called Poisson distribution. I have skipped some steps, but the most important thing was this. So this was limit n tends to infinity, you get e to the minus lambda. That's what this term, and other things are just simplifications. Okay, so this is the Poisson distribution that follows this this PMF. Okay, and this is the Poisson. French mathematician, as usual. French mathematicians were very profound. Okay, and yeah, so this guy he was really good. So his first paper at 18 years age, and then he became professor in 21. I published 300 odd papers. Okay, so this will be the end of the lecture, today's lecture, and I will stop with this. Otherwise, the video splits.